Briefly we're going to demonstrate how to use the ocean optics instrumentation, specifically the spectrometer and the calibration source, for measuring the distribution temperature of an unknown solid source. The first thing you're going to do is you need to measure the source of interest. Currently we have the ocean optics spectrometer, the USB 650, sitting right here, silicon based, with a fiber optic probe already attached, and we're going to measure our source. And as the fiber optic probe appears in the box, it will not have an attachment on it. It'll be a bare fiber. This is not the mode you want to use it in. This bare fiber, as it sits right now, has a particular field of view, and if you remember, field of views are typically associated with radiance measurements. We don't want that. There is another attachment in the box, this little anodized black attachment, threaded. We're going to thread it onto the front of the fiber optic probe here, threads nicely, and at the front of that is this diffuse material that will actually integrate over the hemisphere for the solid angle and set us up in irradiance mode, not a radiance mode. Okay, so we're going to measure our source in irradiance mode. We turn our source on, for example, and we go to our software to see what it is we're measuring. So currently the software Spectra Suite recognizes our USB 650 spectrometer, and it is currently looking at the signal of the source, and it's actually looking at it in real time. You can see it's actually moving here. If I were to move the fiber optic probe in some other direction, of course this would shift. The only thing is, this distribution you're looking at is not calibrated. The system is not calibrated yet, hence the whole purpose of this experiment. So we're going to capture this signal by pausing the software to freeze the frame. We're going to save this out, hitting the save button. We're going to find a spot to save it. Let's just put it on the desktop. We'll call this first measurement of our source or sample, sample. Let's call it sample. And then the couple other parameters we need to fill out. Desired spectrum, we are going to select process spectrum. File type is going to be, there are many file types. We're going to select tab delimited with no header. The columns are separated by tabs, and there's no additional information at the top of the file. In other words, no header information. Okay, we saved that out. We're all set. Now we're going to take a second measurement of a calibrated source, something that's actually known. It's calibrated because in the lab the output of this was cross-compared to another source in which its output was known, so then they could actually correct or adjust to tell you what this source is supposed to look like in terms of scalars called calibration coefficients. Now, if I'm going to turn the source on, and at the front of it is another one of these knurled anodized looking attachments, we're going to remove that attachment with an Allen wrench or hex wrench or whatever you want to call it. There's a set screw at the top. The attachment easily comes out. This attachment is actually different than the attachment you're currently using on the fiber optic probe. This attachment is hollow or clear. There's no diffusing material. This would be, for example, measuring a radiance. So we do not want to use that. When you measure irradiance, you have to calibrate in irradiance. So we'll be using calibration coefficients for irradiance, not radiance. There are two sets of calibration coefficients. Be sure to use the correct one. So we will measure the source, and we're going to capture that with the software. We go to the software, we take a look at what it's measuring. There's the signal it happens to be measuring. We can stretch it a little bit, full screen. We pause it, we save it. Same process as before. We'll save it on the desktop. This one we'll call reference. Or the first one was source, the second one was reference. Desired spectrum and file type are the same as before. We save it, we're done. Now we're going to take one more measurement. Let's turn the source off. Let's remove, using our hex wrench here via the set screw, our fiber optic probe. It's still measuring. We need to take one more measurement. We need to store or measure a dark reference or a dark frame. In other words, the system by itself with no flux on it still generates a signal, we would like to capture that and remove it from all other measurements, including the measurement we made of our source. Simply done. Just cover it up, turn the lights off, whatever you want to do, put a book over it, whatever you need to do to make sure there's no flux incident on the in the spectrometer through the fiber optic. We go to our software, we take a look at what it's measuring. There's some low baseline here. It looks like it's a very small value. It sure would be nice if it is 0, but it's not. We can actually stretch the screen to see what's actually happening. It turns out on the y-axis here, it looks like intensity in terms of counts. It would be nice if this was 0, but it's sitting around 130 and looks spectrally flat from 0.3 out to about 0.9, which is silicon regime. We do the same thing. We save this dark frame, pause it, save it, save it on the desktop, give it a name. We'll call this DARK, dark. Same settings as before. Process spectrum, file type, tab, delimited, no header. Save it, done. Those are the 3 measurements you need to make. Okay. Then once you have the data, they're ASCII files. You can import them into Excel, some other programming language, whatever you feel is appropriate. Okay, so after you've collected all the data, you'll have 3 ASCII files. You need to process the ASCII file that's relevant to your unknown source. You need to calibrate it and assign physical units to it. Right now it's just a series of digital numbers, means nothing. So we need to map physical quantities to that. How do we do that? You pay for a calibrated source that has physical quantities, and you use it to correct or calibrate your unknown source. All right? So we have a distribution associated. Currently we don't have units attached to this, but we have a distribution associated with the calibration source. There are units associated with that, and you can obtain those units. This is the box that the calibration source actually came in. Within the box, there is a CD, lamp calibration data files. This is specific to that particular source. On this disk are a few ASCII files that contain the calibration coefficients. There is a printout of those calibration coefficients on 4 sheets of paper. 2 sheets of paper are the tables, and the other 2 sheets of paper are the plots of the data. Now, there's 2 sheets here because one is for the bare optical fiber, more or less a radiance mode, and the other sheet of paper contains all the data from 300 to about a micron, 300 nanometers that is, out to 1 micrometer or 1,000 nanometers. That's for the cosine corrected irradiance probe. That's the sheet you're going to use. These are the calibration coefficients you need. Okay? They are plotted here, so you can actually look at them. The one on top here happens to be for the cosine corrector data, and the second sheet happens to be for the bare fiber. You could either copy them by hand into your spreadsheet, or you can extract them from the CD. Either way. In the lab, it dictates what you actually do with those calibration coefficients. Remember, the sample measurement and the measurement you made of your source, actually any measurement you made, you'll have to remove the dark noise that you've captured. The dark frame or the dark noise is inherent in all measurements, so you simply can back it out or subtract out that bias. Then you have to perform a ratio in terms of the calibration and then remultiply by your set of calibration coefficients, making sure you pick the correct calibration coefficients. This is what assigns physical units to your spectrum, okay? And it also manipulates the shape so that it is indeed calibrated. It'll already be calibrated for the most part spectrally. You just need to adjust what the magnitude is going to be and where that actually happens, okay? So that's about it. Best of luck.